All right, thank you all so much for joining us this evening. I'm gonna get started with a brief introduction. Thank you to those who are joining us online as well. I'd like to say welcome to our first Love the Lake collaboration event. We're collaborating tonight with Wild Burlington Society, and we'll be hearing a presentation from Teage O'Connor about the connection between trees and Lake Champlain. So Teage is sitting right here. She'll say hi when you come up here as well. Is the executive director of Crow's Path and the creator of Wild Burlington Society, which is a group that meets on the second Tuesday of every month to dive into different naturalist topics and presentations. So a little bit about our organization as well. The Lake Champlain Basin Program is a watershed partnership organization that coordinates and funds efforts that benefit the Lake Champlain Basin's water quality, fisheries, wetlands, wildlife, recreation, and cultural resources in partnership with government agencies from New York, Vermont, and Quebec, private organizations, local communities, and individuals as well. So we have been hosting this Love the Lake speaker series for decades at our office in Grand Isle in honor of Jane Potvin, a past colleague who lived on the islands and loved the lake. So as an LCBP staff member and someone who also attends Wild Burlington Society every month, I thought this would be the perfect opportunity to bring the Love the Lake presentation to Burlington and collab with Teage to reach a new audience interested in some place-based education and learning about the watershed. So I would like to thank Teage, Crow's Path, Wild Burlington Society, and a special thank you to Rock Point Center as well for hosting us here at their new visitor center. Check out the trails and this beautiful area, which just opened. This building just opened to the public recently. I think it's open 10 to 2 every day. And we will have a little bit of time at the end of Teague's presentation for some questions as well. So without further ado, here is Love the Lake.
Hey everybody, so I'm Teage, and I moved here in 2008, and that's when I met Alicia. And I've lived in Burlington ever since, and the lake is just such a prominent feature. I've always lived near water. I grew up in Southern California, next to the ocean, and then I went to college in Chicago, where we had a small freshwater ocean, Lake Michigan, and now out here we have Lake Champlain. But over the years, I've grown from like loving water and mostly animals to starting to appreciate more and more trees. And when Emma asked if I'd be interested in presenting, I was like, okay, how do I figure out how to talk about trees in a Love the Lake series? And so in the talk, I'm going to talk about the lake and the trees. Looks dead. Looks like winter. Oh, am I too far away? Okay. And I'm going to make the contention here that it's not the lake and the trees, but that the lake is a tree. Part of me, when we first came up with that framing, I was like, okay, symbolically, yes, right? The lake appears similar to a tree when we map it out in certain ways. So this is courtesy of Lake Champlain Basin Program. This image here showing the Winooski River and this idea of the lake being a basin. And so we have this Winooski River feeding in with this sort of dendritic pattern of all of these tributaries feeding in the Winooski and getting wider and wider until it hits the lake and dumps in the lake at the delta up in Colchester, Burlington. And so it symbolically appears as a tree, right? So this is a black gum tree. We can see a similar branching pattern kind of in reverse of the twigs extending back and getting thicker as it gets towards the trunk. So symbolically and maybe like as a metaphor, it kind of appears like a tree. Heat versus technology. There we go. But I think that there's a deeper connection here between trees and the lake that we'll draw out. But before we get there, what is Lake Champlain? When I think of it, I have some ideas. But when you think of Lake Champlain, what comes to mind? What do you think of? What is the lake? That's an actual question to you.
Lighthearted is recreation, but deep thinking, it's the heartbeat or soul of the area.
Oh, okay, great. All right.
It's like deep geologic crack that filters water.
Great, that, Colin touched as a tree, as a, plant with a, like a big woody plant with a stick up the middle. It's like kind of, yeah, at a base level. Anything else? Might be something online.
Yeah, it looks like Sophie, if you wanna
Oh.
turn on your mic and contribute online.
Yeah, I've always thought it was my guru, and I've camped out there all summer for 15 years, and it definitely was always leading everything.
Thank you.
The three things that come up for me in thinking about it is, oh, is it back on? There we go. First thing I think of is, I think of it in terms of like an ecosystem. And so the lake itself is made up of the geologic basin. As Pangea was splitting apart, the basin dropped out, and then creates this area where water can pool. So it's got bedrock, it's got soils along the margins, and then we start to add living creatures and plants and bacteria, fungi. We have a freshwater sponge that lives in the lake. And so we have all these organisms that are living there and interacting with the abiotic or non-living factors. So it's definitely an ecosystem. Maybe I should stand on the other side. It's all, too far. It's also a dynamic process, right? So, again, Lake Champlain Basin Program, it's part of a basin. So water or snow drops on the summit of Mount Mansfield. It has two options. It can head east or it can head west towards us. And so it's this slow precipitation or percolation process of water draining down from the Adirondacks, from the Green Mountains into the basin, spending a few months to a few years in the lake, and then draining north to the Richelieu River, and then eventually the Atlantic Ocean. So it's this dynamic process of water moving through here. So it's just a stopping point. It's also a moment in time. So we're giving this, or I'm giving this talk here at that location. But if I was giving this talk 13,000 years ago, I'd be in Glacial Lake, Vermont. We'd be under about 600 feet of water right now. And it would be a very, very different environment with different trees along the margin. I'd probably have to give the talk somewhere in like Richmond at the edge of the lake to make this work. So the lake that we have today is not the lake that we had historically and will not be the lake that we have in the future. Yeah, so it's a dynamic process. All right. So again, back to this idea of the lake is a tree. And this is my dog Boots here. We're out on the lake, and right now, big, exciting news. What just happened to the lake? For the first time since 2019. So if it freezes, that's like this step that we look forward to possibly happening every year. So there are these like cyclical events that the lake experiences, whether it's freezing over or the lake going up or going down. There we go. This is just aerial images. There's a satellite flying over, and every so often when it's over Lake Champlain, it takes an image. So December 5th, then January 24th, February 5th, February 8th, and then February 10th, where essentially most of it is frozen over, except for a few between the widest points, Burlington Bay and Portland Bay in New York. So this is one of my favorite charts that I've come across. This shows lake elevation going from January to December, and this is the average over the last, I'm actually not sure what data period this is from. I think it's maybe the last like 25 years or so.
1908.
This is, that's the dotted line there, that's showing the lowest elevation ever recorded on the lake, which was in 1908. But the actual data, I think, is an amalgamation over like the last like 25 years or so. And then the high water line is here. So this is showing the lake actually sort of like respiring, right? It inhales and exhales. I think of it sort of breathing as the lake levels go up and down. And there's this periodicity to this every year. And this is the amalgamation of that, or the average of the lake elevation throughout the year. So we have 4 main events where the trajectory of the lake changes from either going down to going up or to going down again. So here we have March. We've got this dotted line here. So something changes in the landscape where the lake levels are slowly going down, and something happens around March where lake levels start to go up. and start to go up pretty dramatically. And then they peak sometime mid-April to May, and then they start to go down again until September, and then they rise again. So what is happening in March?
No.
Right, so snowmelt starts to happen, not everywhere. We don't get clear ground until, well, it gets earlier and earlier, but like first week of April is a reliable period of time where amphibians start to move. Yeah, snow's starting to melt. Some of the precipitation that's falling is not falling as snow, it's falling as rain. And so the basin starts to fill again with water rather than drain out. And then we have this weird transition that happens in almost into May. So something happens. Why does our lake level start to go down again? Right? Because we still have the continued, like stuff is melted and then we're not getting snow anymore. We're just getting precipitation as rain. So what happens then that would shift?
It's warmer. Evaporation.
Okay, so it's evaporation. We think about how does water get out of the lake, right? It evaporates out or it drains out, or maybe a deer comes and drinks some and then walks uphill. So there are different ways that the water levels can go up. So that would be one of them, is evaporation goes up. So that's definitely one of them.
Retranspiration.
Tree transpiration, you want to explain
Well,
more?
the leaves come out and so all the trees adjacent to the lake start to pull water.
Hey, great. Got to,
I didn't totally understand what you said.
well, I'll show some. Yes. Yeah.
That's the top.
This is the key here. So spring begins, and then the next big one is leaf out. Oh. And that's the end of that. Any questions?
There we go.
Yes, all right, there we go, okay. Leaf out, and then I'm gonna kind of gloss over, well, fall begins, and that's important once we understand why leaf out is important. And then the last one would be ice up when the lake freezes over, but I'm gonna focus.
And before you leave that slide, Teague, just for context, the lake seems super low this fall. How close were we to that 92.4, do you know?
I think we're at 92.7
Oh,
or something,
really?
we're like just up from that.
So you can kind of imagine what that looked like in 1908.
Yes.
My understanding is that before they regulate the lake more with locks and things, and then it, over 100 years ago, got much lower. And I've seen pictures of them building like structures that's now never above water. Like, for example, out on Providence Island, they've got some pictures of them building cribbing and rock piers that they then later concreted over.
Huh.
And I'm like, it's low water now, and there's still 3 feet of water there, and I was told that they didn't used to regulate the lake as much, they didn't have the locks and the things at either end, and particularly in the south, and so it, over 100 years ago, probably pre-1908, it actually got significantly lower at times.
Huh.
I'm told.
Yeah, okay. Yeah, that's something I didn't know. Okay, so we have leaf out. So why is leaf out important? And this is what Alicia was starting to say. So once the leaves come out, what do leaves for? What's the purpose of a leaf? Photosynthesis, right? And if we reach back to high school or middle school science, to run the process of photosynthesis, we require a few things. What do we require?
Water.
Okay, so we have to have water, sunlight, and
Food.
yeah, you have to have food, but to build the apparatus to photosynthesize, but the actual process of photosynthesis is sunlight, water, and CO2, carbon dioxide, right? So we have to find a way of getting those things into the leaf. So carbon dioxide comes into the leaf through the atmosphere. They have tiny little holes on the bottom or on their leaf surfaces to breathe in carbon dioxide. And where does water come from?
Roots.
Yeah, it comes from the roots, right? Very, very little moisture comes into the leaf through the air. Most of it's coming through the roots, right? So on the underside of the leaf, this is the most exaggerated form of it in our trees that we have. This is an eastern hemlock. And they have these 2 white lines on the underside that are coated in wax. And that waxy layer hides these little dots, which are stomata. And those are the pores that allow carbon dioxide to come in. And when they're open, they also allow water to escape. And as water escapes, every little droplet of water or molecule of water that escapes draws up a little bit more from the roots. So as soon as the leaves emerge, and these are here throughout the year, so we'll go back to our Norway maple. As soon as our Norway maple leaves out, opens up, it starts taking in carbon dioxide through the stomata on the underside of the leaves, and it starts to also get rid of water, and it draws up more water from the roots. And so as soon as these leaves are out, that process of sucking water up from this soil begins. And about 95% of the water that is absorbed through the roots just gets evaporated out to the rest of, or to the atmosphere. The rest gets incorporated in the process of building the sugars themselves. So as soon as this happens, and imagine like what it looks like. Okay, so imagine that wall mural over there that's covered with these beautiful trees. As soon as those plants start to photosynthesize, every one of those leaves is pumping out water that's being sucked up from the soil. And that prevents, for all the trees that are dotting the landscape across Vermont, that prevents that water from percolating down through the soil into the rivers, eventually making their way into the basin. And so if we look at this, it has a profound impact on the lake ecosystem, going from around 98 feet on average down to, when the leaves start to shut down, about 94 feet. So we lose 4 feet of water, yeah, every year to this. Okay, so in 1982, this guy, Richard Dawkins, wrote this book called The Extended Phenotype. And I'm going to kind of apply this idea here to trees, and it's not exactly one-to-one, but his argument is that plants, animals, organisms have genes that code for stuff to build the body of that organism. But they also have some genes that code for the behavior outside of their, or structures that they create outside of their bodies, or behaviors in other organisms. So for example, a bird does what every spring? It builds a nest. So it has something genetically that codes for the ability to, and the propensity to build a nest. Beavers build lodges and dams, and other organisms like some parasitic flukes will change the behavior of their host species of fish to make them flash their bellies and make them easier for osprey to eat, and then the osprey, the fish, poop out the parasite that was in the fish somewhere else, and their life cycle continues. So this extended phenotype is something coded into an organism, changing the external behavior of things around it. So I was thinking about this principle of trees, sort of these genetic components of trees, and then their behaviors changing the world and ecosystems around them. So how does this play out?
It gets drier.
Okay, so it does, it gets drier. So we saw that in, striking, portrait this fall when all the lake was so low. So some of the things that the trees do to the surrounding environments is we have erosion. So with trees, there's sort of two different types of erosion that they perform on the surrounding areas. The first is, oh, you can see it when you're standing. Off to the side, it's not quite as clear, but the first one would be mechanical erosion. And so this is a white cedar tree here, and you can see the roots anchored in place, and there's soil around the roots, and there used to be a rock here. And then there was a rock with a little crack at the top, and then soil would fall off the cliff. This is Mallets Bay, and soil would fall off the cliffs, wedge into that little fissure, the roots took hold, anchored the soil in place, and then the roots expand and they exert a tremendous amount of what's called turgor pressure, which is when water fills the roots, they expand, and they can produce a tremendous amount of pressure that actually fractures the rocks away from the wall. So this rock recently fell off, so you can see the exposed surface in a different color, and then the soil is still anchored in place. So the roots of these trees are able to wedge down into cracks, and then as the roots grow, they're able to fracture off these rocks. So we got her. So here's in sort of a side view of another rock being pulled off slowly from the cliff surface. There are also bacteria that live on the surface of the rocks that the roots are able to create a nice substrate for, so that the bacteria can decompose the rocks. And in these rocks, we have calcium, we have magnesium, we have these other critical components of the plant body that then the bacteria are able to make those resources available to the tree. We have another one that does the same thing. This is staghorn sumac, and I was able to trace the roots from this staghorn sumac probably about like 30 or 40 feet through the rocks in these little cracks. So then what's the end result of that, right? We then have these rocks fracturing off, and as the rocks fracture off of the cliffs, they create this incredible underwater ecosystem. And so we have rock bass that live in there, and we have bluegills and pumpkin seeds that are foraging in this. Actually, I didn't include a video here. This is also at Mallett's Bay, but of perch that are feeding on the algae that grows. This is filamentous algae, sort of, yeah, on the rocks. And so the perch are like feeding on that, and for macroinvertebrates in between that. So we're creating these little underwater ecosystems that fish are able to take advantage of. It also creates, so here at Rock Point, if you go out, it's rocky along the edges, and then it's pure sand going from Rock Point over to, okay, so going from Rock Point to another point up that way, Apple Tree Point. And if we look, that creates conditions that this is a male smallmouth bass defending its nest, and they only nest on places that have rocky substrates. So 10, 15 meters this way, it's all sand. So the trees decomposing the cliff edges and providing this nice, supply of rocks, then the bass are able to nest in it, right? So
He's like he's pretty.
oh, yeah, this is a time lapse, so it's sped up. But they do this.
Where is the nest?
Everything that's clear, you can see how it's dirty back here. They will like flash their tails and kick up all the sediment off of the rocks to clear out the nest. And the males wait there, the females will come and inspect the nest, and if it's a good nest, they'll mate with them. And then the males don't feed for like 2 weeks while they just defend the nest. And they just spin around all day on snorkeling at night, and they're there at night defending the nest also. So it's like a constant.
Taking the dirt off all the time, aren't they destroying the nest?
So they, these are their eggs, and the eggs are like loosely attached to the substrate. Yeah.
But they don't move.
The eggs no, the eggs don't move. Yeah.
Interesting.
This is a spiny cheek crayfish, and I think I actually took this the day we went snorkeling down at Shelburne Bay. And yeah, so there are these rocks there. It's not as dramatic with the trees crumbling the rocks off this cliff edge, but same process of creating habitat for crayfish to be, yeah, nestled in these little rocky crevices. There's another organism in there, another animal.
A clam or something?
Yeah. There's attached to its body are a bunch of, this is a female. Females for most crayfish only molt once a year, and the females tend to get zebra mussels on the longer lived individuals.
Oh.
Yeah, so there's 1, 2, 3, 4, 5. Yeah.
Oh.
So another thing that trees do to influence the ecosystem is they produce pollen. This is in late May, I think, and this is mostly pine pollen. And pine pollen, it murks up the water, so it makes it hard to see when you snorkel this time of year, which is too bad. But it provides great forage for lots of animals. So these are tadpoles from wood frogs, and they'll graze on the pollen grains. I've also seen, this is a snail, and I don't know what kind of snail it is, but I've seen these on the like upside down on the surface of the water, grazing on pollen grains in the spring.
They
It's just
look like a slut.
yeah. So a pretty cool little pattern there. So pollen providing an input of nutrients. And one of the things, and I couldn't find specific information on this, but in river ecosystems, like 99% of the available energy and nutrients is what's called allochthonous, which means it is generated outside of the river ecosystem. And I couldn't find numbers on what it is in lake ecosystems, but lake ecosystems are not that efficient at primary production, which is like photosynthesis. So most of the energy and nutrients that are available in aquatic ecosystems, whether it's a river or a lake ecosystem, is going to be allochthonous, allo, other, and chthonous means produced in Greek. So these are resources that are coming in from the outside environment, largely trees, because most of the biomass in Vermont is made up of trees. So we get it from pollen, we also get it from organic material. So this is, I think this is a large cottonwood tree here up at Delta Park. This is upriver from there. This is the Winooski Dam. In 2019, we had that incredible Halloween storm. And I went down to the river afterwards, and this is what's being brought downstream. And where does all this stuff wind up? Eventually, it winds up in the lake. Here's my poor dog Boots. Thought it was a trail. He's totally fine. Yeah. But you can also see in this, look how brown that water is. So it's not just that the river is bringing organic material, it's also bringing heaps and heaps of inorganic material down with it, which we'll get to in a little bit. And then here's ultimately what happens is those logs are washed all over the lakes. I used to, when I lived in Southern California, the Shumash there, they had two different types of canoes that they would use. They would use one that they made out of reeds and the other that they made out of redwoods. And where I was in Santa Barbara, we don't have redwoods. So how are the redwoods getting there? They're not, cutting them down and then paddling them south. The redwoods would just wash up and they'd be like, hey, we got a canoe. So here's a similar process where you have the Winooski River and these other major rivers drawing in these large organic objects that then become substrate for, in this case, zebra mussels, but also for lots of macroinvertebrates that are laying eggs on there, foraging algae that develops on there. This is another view. Maybe it's a little bit hard to see. The lake, what color is it? You think blue, maybe if you were to draw a picture, but it's like brown often. And this was after the 2019 flood, where all the sediment from around the region had just been washed in.
Where,
This is up at the top of Mount Philo, looking down.
oh, but I was trying to figure out where it was.
Yeah. So kind of the inverse of that of like the trees providing a source of input into the lake, we also had the opposite capacity of trees to inhibit the flow of water into the lake. So this is an aerial image. This is Wheeler Nature Park? What do they call it?
That's right.
Okay, Wheeler Nature Area, Nature Park, something like that. Yeah, sort of the delineated space of that. And this is in 1937, and this is generally what Vermont, a lot of Vermont looks like in 1937. Well, Chittenden County looks like in 1937. It's all farmland. And if you have farmland and you're tilling it, or you have cows that are overgrazing in an area, then you don't have roots that hold the soil in place. Think back to the white cedar on the cliff edge, holding soil in place on a cliff. Now imagine on a flat area, the ability of roots to hold soil intact is significantly higher. So we have farmland all over, so flooding events had a lot more of a devastating impact because it would rain and more water would enter into the waterways. So it's not, maybe this is sort of storytelling lie a little bit, but if you look for water channels here in 1937 and compare it to 1974, you can see these sort of exaggerated lines. And maybe that's not actually true in this image, but as a general trajectory of areas that don't have vegetation, you have higher rates of erosion. So I talked about like the lake was here 13,000 years ago, and 14,000 years ago, there weren't plants here originally once the glaciers were treated. And because there weren't plants, if you look at sediment layers in the lake, they're thicker and thicker and thicker, and then once plants arrive, the layers get thicker or thinner and thinner because plants are anchoring the soil in place, and so erosion isn't as big of a factor. So trees along like riparian buffers are important to hold soils in place. Conservation law, plant trees. Okay, so the inverse is also true. So the lake is a tree, but a tree is also a lake. And not all trees are, but like the trees that we have growing along the lake, because the lake is a unique ecosystem, you have trees that are able to compete along the margin of the lake that are different from just a few feet back or a few hundred feet back from the lake. So what makes the lake such a unique ecosystem? So first thing, lake moderates temperatures. So it is generally in the winter warmer near the lake and colder farther away. Water is much better at holding on to heat than land is. And so it creates a more stable environment. If anyone ever saw the movie LA Story with Steve Martin, he's a weatherman in Southern California. The big joke is he just has these little magnets that he throws. And he's like, it's 70 and sunny, 70 and sunny, 70 and sunny. And so everywhere in Southern California along the coast, 70 and sunny year round, because the ocean is this huge body of water that just moderates the temperature and keeps it more stable across yeah.
That's why they have a lot of orchards in the islands. Because we don't get the first hard frost until weeks after the rest of the state.
Yeah.
Because we're in the middle of the lake.
And I'm in Burlington, and when I first moved here, I was like, oh man, I can't plant stuff. And then I was like, wait, it's like actually warmer. So I have like peaches and apricots, and it's just, yeah, much warmer than, 15 miles away. And yeah, Underhill, Jericho.
Yeah.
It's very different.
Planted apricots in Burlington?
Yep. Yeah. I also have a walnut though, and the walnut is what's called allelopathic and basically kills all rose family plants. So as a producer, it pushes
They
up.
leach a toxin into the soil.
Yeah, that's allelopathic.
Competition.
Yeah.
They also, walnut shavings will kill a horse if you use it for bedding.
Yeah, don't do that then.
Those are
Yeah. So this isn't like a real scientific comparison here, but Burlington and St. Johnsbury are the same latitude, and this is just a comparison of the temperature of those two areas. And mostly what's important here is the lake is a regulating factor in the winter, and there's other factors, I'm sure. What I wanted is the better comparison of like Burlington to Richmond, a gradient there, but I couldn't find the data. But the average low in the winter, 28 in Burlington and 26 in St. Johnsbury. So I just put this up as like an illustration of the capacity of St. Johnsbury, which is on the other side of the Green Mountains, the ability of the lake to sort of buffer Burlington and keep it warmer. One of the bigger differences about growing peaches and whatever else is not necessarily the average low, but about the growing length. So when the first frost is and the last frost, and as you might expect in Burlington, it's a longer growing season, a longer space between the first or the last frost and the first frost. Another thing that you notice, maybe if you spend a lot of time on the lake, is the lake often doesn't have clouds over it. Right, and so it's this cool pattern where the lake, again, is a reservoir of heat. It is a more stable environment, and you tend to get cloud formation happening when you have different types of air colliding with one another. So we have stable air over the lake. You tend not to have clouds versus if you have like a cliff where air goes up, or you have exposed rock or a big quarry or something, and then next to it you have a forest, or you have a hardwood forest next to a softwood forest. You have these different microclimates that are radiating different amounts of heat, and it creates unstable patches of air that lead to the formation of, like in the background, these cumulus clouds. So it's also creating an environment right around the edge of the lake where there's just more incoming sunlight because there are less clouds. In Vermont, cloud cover is what creates those little bald spots up at the top of our summits. Alright, this isn't a common occurrence, but it's magical. So you kind of get this marine layer sometimes when you go from Burlington into Richmond, like in the mornings, where the cold air will settle down and create this really cool pocket of clouds. But this, did I put the conditions on here?
You say flurry.
Okay, so this marine layer, we used to get this all the time in California, where you have a marine layer in the morning, and then in the once the sun came up, it would sort of burn off the marine layer. Here is sort of the opposite. This is sunset, and so this was in May back in 2012, and so the temperature was really cool. It was a normal spring, so in the 50s, and then the temperatures jumped to 70s really quick. And so a lot of moisture evaporated. There was like a lot of moisture in the air, and the lake temperature is about 40 degrees. And so right at this surface here, the lake is much colder than the warm air, and the warm air near the lake surface cools. And when it cools, like imagine you have a glass of lemonade, what happens to the cup in the summer? You get that layer of dew that forms around the edge. And so this is like a layer of dew that forms on the surface of the lake, where you have this interface of really warm air and a really cold surface.
When was this? Fall,
May,
spring?
this is May. And May, you can still see like flower buds on that one.
Isn't there something also about the surface of the lake then starts creating clouds right above the surface? I thought
I
that,
heard that called like lake effect clouds, is that the?
I don't know, LCC used to ask me to look for that and photograph for them, because it didn't happen there.
Yeah.
But it might not be what you have there, I don't know, it's it was almost like a little cloud spiraling on top of the lake.
I have seen it.
Yeah, I don't know if that has a specific name, but those are like more wispy.
It was just something I wanted photos of.
Yeah. Yeah.
So I had to watch for them, and you have even better there. I'd like to get out of here.
I'm just doing a quick time check.
Oh.
So another thing we do get is lake effect snow, and this is more common on larger lakes like Buffalo gets these crazy storms that'll be like 12 feet of snow. But we do occasionally get this. There was one in Cornwall back in 1996. And what happens in these events is you get these like cold Arctic blasts of air, and what is Lake Champlain, like 125 miles long or something, and then at its widest,
9 or 10.
yeah, maybe 12 across at the very widest. But it's this long chute, so as cold air blasts down through here, we have this relatively warm lake surface that moderates temperatures here. And so you can get cold air that blows over a much warmer area. And as those two bodies of air collide, you can get this like dump of snow where it's like 2-3 inches an hour for maybe an hour or several hours. And so right along the margins of the lake, you can get these intense snowstorms. So what impact does that have? Well, trees that are right along the margin can get a lot of snow really quickly. Not a big deal for most of our trees that are hardwoods, but for conifers that have needles in the winter, that can be a big deal for snow loading. Yeah, so another feature of the lake that makes it a unique ecosystem. So some of the things that it provides, both benefits and I guess not benefits, challenges in the environment. So nutrients, we talked earlier about leaching of nutrients. Water is slightly acidic. This is a bathtub ring around the lake on the cliff edges where you can see this sort of whitewash here. And this is a zone of leaching where ice spray and like ice damage loosens up the rocks there. And then there's bacterial action that can then release calcium. And so you have this, it's not a material that's pasted on, but it's material being removed. And yeah, so you have calcium that's being drawn into the lake system. But also that's then being pushed up on shores and along the margins. You also have these major flooding events, or just in like river delta ecosystems, but also as the lake goes up, you have sediment being deposited in areas where there's not a rocky bottom or a substrate, but a soft sediment substrate like sands and silts and clays. So this is, I didn't have a great image of it, but this is a cottonwood tree with beaver in a very ambitious beaver here, trying to take down this tree. And one of the things you can maybe kind of start to notice is these are the roots here, and there are significant sized roots. And there's like one here, but as you go further down, there's more big roots lower down. And so these trees are extremely fast growing, and as sediments build up, the lower roots drown. They run out of, the water table also comes up, and they run out of oxygen supply, and they also just get buried in sediments, and so they send out roots higher up and higher up and higher up. So you get this sort of like terracing of roots as sediments build up in these delta ecosystems where cottonwoods love to grow. Here's Boots. I like that there's like dynamic photo, right? You can see the wind blowing, flapping his ears back. So he did not want to pose for this photo. It took me a while to get him to sit still. And the wind was probably blowing about 35 miles an hour. This is in, I don't know, a couple months ago or so. Yeah, but winds are a big problem for challenge. Okay, it's a big challenge for plants on the edge of the lake, but if they can overcome it, there aren't that many plants that can overcome that as well. So if you can meet the challenge, then there's not as much competition for you. So there are two different ways that plants have to contend or can contend with this. One is in the summer, when winds are blowing, they have to be able to retain moisture on the leaves. So this is spotted jewelweed or spotted touch-me-not. And I use this as a visual example here. You can see water beating up on the surface. So they have a layer of wax that they exude. All plants have a layer of wax, a cuticle. On these, they're these like little crystals, nodules that are, it's called super hydrophobicity. So very afraid of water. And it makes them extremely repellent to moisture so that it beads up and it draws anything that's on the surface, so dust, spores, etc. But the other thing that it can do in the surface of, oh, whoops, I don't think I went that far. Maybe one more. Okay, this is a silver maple leaf, and I just took my thumb and I kind of rubbed it, and so you can see how it has this. The white is the silver. When the wind blows, it kicks up the leaves, and they show their white undersides. And it's this waxy cuticle that covers those stomata that I showed on the hemlock leaves at the beginning, that are where carbon dioxide comes in and out of the surface of the leaf. So to resist drying out in the summer, they have this waxy cuticle. In the winter, it's just as much of a problem for twigs, not for leaves. So this is box elder here. You can see this thumbprint. I just pressed my thumb on it and then pulled it off. You can see it's perfect fingerprint in there, and you can rub it off really, really easily. And it's the same thing where they don't have stomata, but they have these, which are called lenticels. And those lenticels do the same thing where they allow for gas exchange to happen. So they need to prevent drying out in the winter.
But your thumbprint looks remarkably like this cross section.
Isn't it tricky?
Oh, yeah,
It totally, I
Oh, it
would
does.
have never known that was a thumbprint.
I'm part three.
I think,
Yeah.
yeah.
So the other challenge that plants have to overcome is ice, and plants aren't growing, or trees aren't growing in the lake for the most part, but in flooding, they can be in the lake. And so you can see this sort of circular pattern as these rafts of ice are getting pushed around, and
I thought that was just mildew.
so here I have a camera that has a time lapse on the bay right down here. This was 2023, which is a terrible year for ice on the lake. But you can kind of see some of those chunks of ice that were there for a little bit, and they get pushed around. But if the lake is higher or there are trees that are growing lower, those chunks of ice crash into the trees and can damage the bark. So here are cottonwoods that have ice damage on the trunks. So a tree has to be able to heal itself and deal with the effects of ice damage. Or trees, there was also a bunch of woody material that's also bouncing around during the rest of the year that can knock into trunks and damage the trunks. So ice is a problem, but it's also a problem in a different way, where you have super cooled water, so water that's slightly below freezing, but if it's moving around, it won't freeze as easily. But if it sprays, if waves crash it against the rocks and then the water sprays up, it knocks into trees and it can freeze on them. So you get ice damage of the trees that go right along the shoreline. White cedar, this is northern white cedar, it's really capable of dealing with that. Some of the thinner branches are very pliant. They can bend with that and sort of bow down. And I have a hedgerow of cedars next to my house, and it's typical for them to bow down like 2 feet or so and then rebound just fine.
Nice picture.
Yeah, thanks. Yeah. Alright, so another thing that the lake does for trees is seed dispersal. Anyone know this one?
A tree of heaven or something?
Oh, it does look like Ailanthus. Ailanthus tree of heaven has these long bean pods. Yeah, and we have Ailanthus here. There was some on I-89 going up to Lake Champlain, but it's invasive species and the state cut it down. Yeah, but it's not this.
Butternut?
Yeah, this is butternut. And butternut's a riparian species, so it grows along rivers and other waterways where there's like nutrient enrichment. But it also is dispersed by squirrels and jays, maybe? No, probably not jays. But yeah, rodents. But also if it falls into water, it can float. And I often find butternut, the husks of it washed up on shore, sometimes with zebra mussels.
How big is that about?
Life size? That's probably,
Like one of those nuts.
yeah, I think this is probably about life size.
Don't get that,
Oh,
don't get
Yeah.
that big or real big,
Yeah.
maybe that long.
It's related to walnuts.
okay.
It is, white walnut is another name for it,
Oh,
yeah.
yeah. Does it taste good?
Yes, delicious. Also had seed dispersal here. This is cottonwood fluff that's on the surface, and so it doesn't, on calm days, it doesn't break the surface tension, and so it can get floated around very far. So seed dispersal is important for it. We also get this sort of a lot of riparian and lakefront trees drop their seeds in the spring flooding when water levels are high, and then water levels drop, and those seeds are deposited at the margins so that they don't drown in the water as lake levels go back up again. So these are silver maple. You can see the fruits or samaras here, and then the little seedlings that have germinated up out of it. And this is the Winooski River. But you can see like the river has gone down and all of these fell in April or like first week of May, and they fell into the river floods, deposited all this fruits up on the high water line. Most of these will die, but if flooding is really high, it deposits them up here in a place where they might be safe from future flooding events.
I wonder who put the fire.
Another thing that happened, so this was kind of a cool find. I was snorkeling out here, and there's a little willow twig. And I don't know what species, but some sort of willow twig. And willow twigs are really easy to snap off of the branch. And part of the reason for that is they're very capable of producing gibberellin, which is a plant hormone that stimulates root growth. So if this gets floated somewhere and then stuck in mud, it can generate roots and start growing there. So yes, they can, these are the little fruit capsules here that can generate seeds that reproduce that way. But they can also reproduce vegetatively, which is a cool strategy that a lot of riparian species have. Riparian just means growing along rivers. Okay. I just have 4 more slides, so I'll go quickly. But I mentioned earlier that the lake is like a unique ecosystem. It has unique characteristics that create conditions for trees, different species of trees, to compete along the lake margins that they can't necessarily compete outside of those conditions. There tend to be, I think, maybe like 4 kind of zones that the lake creates that allow for different communities of plants to grow in those areas. So the one would be cliff margins. So this is here at Rock Point. Oh, yeah, right there. There's a bigger photo of it. And so we have these cliff edges. This is mostly made out of calcareous or calcium-rich bedrock, and you tend to have like hop hornbeam can grow in there, but it's like mostly white cedars that can compete on these really, really dry soils with rough conditions throughout most of the growing season.
Is that a hydro house that you did?
No, this is Lone Rock, and then this is another massive rock that's out there that's just chunked off of the cliff and fallen in there.
Oh, weird.
Yeah, so we have cliff ecosystems. We also have soft substrates. So these are ecosystems that are made out of sand and silt and clay. This here is a unique ecosystem called a lake floodplain forest, lakeside floodplain. What is it?
Lakeside flood.
Lakeside floodplain forest, yeah. So we brought a canoe and paddled around here while we were looking for fairy shrimp. Yeah, so a unique ecosystem, and there's this little like retention wall of sands that get piled up as like a little mini dune, and then it captures water in the spring, and so it floods this area, and then by the end of the summer, or by the time all the leaves have come out, that starts to dry up, and in the fall this is like totally dry. But because it floods, it creates conditions that only certain plants that can tolerate flooding, American elm, black ash, grow in these places, and other species can't. We also have deltas, and deltas are, they tend to have a lot of water, so this is Winooski River Delta. But they're also just much more dynamic than the other floodplain forests where you have flooding, but you also have a lot of like destructive power behind that flooding. Whereas the flooding that might happen here is just like a slow accumulation of water in the spring, but not like a powerful destructive force like I showed earlier. Yeah, at the Winooski Dam. So delta is also unique ecosystem. Also these islands that are really, really cool spots because they have like usually a fringe of cedars that are growing right along the edge where you have that ice spray, and rocky, shallow soils. But once you get on the interior of them, they're these strange, really, really dry, different communities that have like red oak, white oak, hop hornbeam, and some real characteristic like island species. Yeah, this is Schuyler Island, which is like straight across the lake.
Are there any buildings or?
It looks like there's an agricultural history. I don't know the history of Schuyler Island. Most of the islands were inhabited at one point or another. Like some had livestock or small.
Islands were cheap real estate in the 30s and 40s because most people farmed. And you could buy an island cheap.
Well, you couldn't go
They're one
on
more-
land
that's
or get any stuff, did you, for example?
Oh, that's it.
That's it.
Okay, that's it. All right. Yes. All right. Okay. Cool. So, yeah, I'll open it up to questions. 7:29.
You've got 30 seconds.
30 seconds.
I have a question, but I have a comment. I
Yeah.
really liked that, throughout the year, what happens to lake level and the connection that you made to Leaf Out. I sort of, it's in the back of my mind.
Yeah.
It's nice to see it so clearly described.
Yeah.
Yeah, what a great.
So I had a question related to that. So if this state was like 80% agriculture and maybe 20% forest, would that have impacted that beautiful curve?
Yes.
There's.
Well, and it was, the state was 8% deforested during the century.
Yeah.
A little bit more.
So, what's the like productivity, the NPP, net productivity, photosynthetic productivity or something like that of an ecosystem, like a forested one versus like a grassland? Because it's not like forests are evapotranspirating, losing water, but so are like agricultural fields. So then you would have to compare those. And then you would have to compare that or factor in like the amount of erosion and water that would have gone in. I honestly don't know. I know it would have been different, but I don't know how it would have been different.
You'd have
Yeah.
more
I don't know.
evaporation. You'd
Yeah.
have more evaporations in the summer. Because you have no trees.
Yeah, so you'd have more soil evaporation because, yeah.
I think your gland, the whole thing would be warming.
I don't know. Yeah.
Well, think
I think
about
it's
how
like-
cool the trees just really make the land cool.
Yes.
And, and it's nice to be in the trees.
There's also like an added layer of complexity to trees where
Yeah, when you go
water
down.
doesn't just land on the soil surface and then either go in or wash off. It lands on the trees that then slowly drips down off of leaves. And so there's, yeah.
But if you're 95% no trees, which is what Vermont was at one point, I'm just saying, I bet it was a lot warmer. Because when you go where you are with trees, and then during the summer, you go in downtown where it's all asphalt, it is 10 degrees at least.
Like a
warmer.
very good data investigation.
Yeah, sounds like a very peaceful process. Yeah.
It wasn't,
Like a
wasn't
basic
much
program.
data collected back then, it's a
Yeah.
problem.
We'll have to get. creative.
Yeah. Other questions? Yeah, Wilbur?
I have a question about the fall on that
Yes.
line. Can you just chat a little bit about what the tree?
Yeah, do you wanna go back to the chart? Yeah, so essentially what happens is the opposite trajectory, right? You have, okay, so, looking here, we have leaf out and then we have evapotranspiration as things are photosynthesizing. And then in the fall, photosynthesis starts to shut down in leaves and leaves are starting to be shed. And so what happens here is not necessarily that there's like an increase in precipitation, but that there's less water loss from the environment, from trees and non-tree plants. And so at this point, as roots start to shut down, more water is making its way into the major rivers that are feeding into the lake. And so the lake levels start to rise. And then what happens here is lake levels slowly start to drop, but barely, and basically stuff is just in stasis where water that's leaving is roughly equal to water that's entering. And most of the water here is this, it's snow, it's ice, the soils are frozen. And so there's just sort of this like stasis of lake levels. Yeah.
And then with like the drought that we got like this past summer and it led to like fall happening early.
Yeah.
Does that have like an impact, do you think, on like the water uptake of those trees?
Yeah, so what happens is the fall happens earlier because you have we have flash drought, and so essentially trees are like, I don't know how long I can make this, so everything kind of shuts down. So their stomata stay closed, they're not taking up CO2, so photosynthetic rates drop, and then they eventually just like cut their losses, and the stress of maintaining a leaf, the leaf can no longer like pay for its own survival, and so we have like an earlier fall. It's also a more subdued fall because plants produce red colors in the fall. If they have less stored energy, they don't have as much to spend on those anthocyanins, so it's like a more muted fall. But yeah, so there's like a lot going on where we're not getting rain, so there's nothing to go into the rivers to feed into the lake, but we also have less evapotranspiration. But in that case, like there's a bunch of different factors and they kind of shift like which one's the most important. And in that case, it wasn't the leaves, it was the lack of rain that was the most important, that was leading to a drop there. Yeah. I think maybe we'll wrap up there and then I'll stay and you can ask me your question.
Okay.
Yeah.
All right, well,
Thank you.
let's all give Teague another.